There he is, the legend, Charlie the dog, sleeping in his enormous bed. And then, just to give you a scene, got we got Jules the cat hanging out, being cool, cooler than cool. So, yeah, we'll give Jules some, we'll give Charlie some time this time. Get some calming Charlie vibes today. Get those Charlie vibrations. All right, cool. So let's get into it, shall we? Shall we? Uh-oh. Uh-oh. Excellent. All right, here we are. Here we are with graphs. So today we're talking about graphs. Not this kind of graph, but I think this is delightful. It's a bird one way and it's a cat another. Nice. All right, so first I start with a disclaimer. I love graphs. If you thought I like trees and hash tables, you haven't seen anything because graphs are fun. They're amazing. I've done research on graphs for language understanding. I've developed large-scale graph databases in industry. In middle school, when you open up my locker, I just had pictures of graphs in there, just really nice graphs, really strongly connected graphs, you know? Like, I'm just all about graphs. I love graphs. Graphs! Graphs. Gra- graphs. All right. Here's one. That's a nice graph. Very floaty. It's out there doing its thing. It's floaty graphness. So here's the fun thing about graphs. You could argue that all of the data, we could argue, and it's just true, all of the data structures we've covered thus far are some specialized kind of graph. So they're sort of the greatest grandmommy data structure in the sense that they have everything can be described as a graph, just like how it's like we've been learning about circles, rectangles, pentagons, parallelograms, and now we're finally saying all of these things are what's called a shape, right? So today we have something where it's, balanced binary search trees, hash tables, lists, um heaps, so on and so forth, are graphs. They're kinds of graphs. So let's get ready for some connect the dots. Yeah. All right. So graphs in general are used to store information about how different entities or concepts or objects or points of data or whatever, how they relate to each other. So graphs are, if we think about trees as being sort of a family tree that's very hierarchical, graphs are like decentralized trees. It's graphs are everybody every node in a graph can have some amount of relations to other nodes and itself, which is pretty interesting. So it's a generalization of these other data structures we've talked about it. Graphs, each graph has a vertex, and the vertices or nodes, you'll hear me use that interchangeably. Vertices and nodes are connected by edges. So if you think of connect the dots are vertices or nodes, and then the lines that connect them are the edges. Vertices and nodes store data and may have unique keys. So typically vertices have some amount of data in them, and most commonly that data is represented as some kind of key value store. Um, so which is why you could view a hash table as either a collections of key value nodes that have no edges between them, or you could view them as one node that has an efficient key value store in it. Eh. So edges connect one or two vertices. So an edge either connects a vertex back to itself or connects two vertices. They cannot connect three vertices. Now, there's a way if you want to do that you can cheat that out in a sense. You basically make, instead of having a vertex that connects three things, you make that relationship a rather than have an edge that connects three vertices, you make a vertex and that represents that relationship and connect it to all of the edges. So there is actually a way around this without breaking the rule that a vertex, or sorry, an edge connects one or two vertices. Um, Typically this connection conveys some kind of relationship about how the two things connected are related to each other. Edges can also be used to store data. They can also be key value stores. Um, so here's some common data an edge would have like a name, like type or class to it. Have a weight, which would be some numeric value that represents how much of that relationship is involved. For instance, the most common weights you'll see is if the edges represent like spatial distance. Like if I have Baltimore and Washington D.C. and there's an edge between them that's however many miles apart they are, right? So you can make a graph that represents the distance of locations from each other, where the edges all have the weight of the actual physical distance between them. But it can be like intensity or um timestamps, like when that edge was detected, and so on and so forth. Also, they can and frequently do have direction, meaning the edge goes from one node to another node. Um, and so if they're directional, that usually represents a non-reflexive relationship, meaning it doesn't go both ways, right? So um, your your parents are parent like they're your parents, so they would say like has child and you'd be there, and then you'd have has parent, but that doesn't go both ways. Whereas siblings is reflexive. You and your brother or sister are both siblings of each other, so you would either have an edge with an arrowhead on both ends, or if you're in a graph where all relationships are reflexive, for example like that distance graph where if I'm 20 miles away from you, then you're also 20 miles away from me. If every edge is bidirectional, it's called, then you don't draw any arrows. It's just a bidirectional graph, and all the edges just don't have arrows on them. Okay, so here's a cool graph. I hope if you've watched Game of Thrones, this isn't a spoiler. But let's look at this graph in a little more detail. So all of the blue nodes here represent characters. All of these like hmm, I guess you'd call that like an reddish orange red hue would represent families. Then organizations are yellow. Uh Purple is a crime, and I guess this pink color is a location, right? So all of these edges then are directional. Oh, and titles. The gray is titles. All these relationships have directions because they have arrows, and you can see they all have different meaning. Like presides over, is a member of, has committed high treason, so on and so forth, right? So what you can do then with this graph is model all the relationships between entities in this story and how they relate to each other, and you can start to do some queries. So here we can see Tyrion Lannister was accused and condemned of regicide and kinslaying. So spoiler alert. um, but it's not that big of a spoiler. So there's two ways of implementing a graph. Two ways, or two main ways we've implemented stuff in the semester. What are they? Well, it's arrays, right? We've either just stored stuff in an array, or we've stored stuff in some kind of linked structure, like a linked list or a linked up tree, basically where you have like a node based pointer structure and then you have an array structure. Are graphs any different? No. No, actually they're not. We're going to use both. We're going to talk about two different implementations of graphs. So let's like whenever we talk about, so we've talked about an abstract data type where we have vertices and edges. We're also going to talk about two methods. Um, so one method, get edge, where I give it two vertices, u and v, and it gets the edge or edges between them, um, if it exists, null otherwise. And in the case of a directional graph, it would only give me the edges from u to v. Um, then there's get neighbors, which we give a vertex, and it will give us all of the neighbors of V. Again, these would be neighbors that edges go out towards, that you all the places that you can reach from V. Um, but here's what's fun. Here's what's really fun about talking about asymptotic analysis for these data structures is we don't just have a size, one variable to think about. We have two. We have the amount of the amount of vertices, which we make like pipe v pipe, or it's like the cardinality symbol. We have the number of vertices in our graph, and we have the number of edges, because I could have a graph with, because they're independent of each other, right? I could have a graph with a large amount of vertices and a small amount of edges. I could have a graph with a million vertices and no edges, and I could have a graph with two vertices and hundreds or thousands of edges, right? Because there's no limit on the number of edges between two vertices. So rather than just combine those figures into n, we're going to leave them independent of each other. And what that's going to be interesting for our analysis, because it'll allow us to prefer data structures when we have more vertices and less edges, or when we have more edges and less vertices. So let's talk about the first one. It's just a matrix. It's just an array of arrays. So what we do is we keep a two-dimensional array where um the amount of rows and the amount of columns are the same as the amount of vertices in the graph. So if there are 5 vertices in the graph, you have a 5 by 5 grid matrix. If there's 10, then we have a 10 by 10 matrix. If there's 100, then we have a 100 by 100 matrix. Then what we do is we say that um, if if we look at the rows, we'll look at, or maybe the column. It doesn't really matter as long as you're consistent. If we look at the column for one vertex and we go to the row of another vertex, at that spot we will store all of the edge information about an edge that connects those two things, and we'll leave it blank if they're not actually there. So here's an example, right? So we have this graph here, and so say our edges, there's no special information about them. We just want to store, are they there or not? Like, are these things connected in this way or not? So what we could do is we could say, okay, 5, we'll look at row 5, and then we'll look at column 1 and see, oh, there's an edge there. So if I covered this up, so what we would want to see is there an edge connecting 1 and pointing it to 2? 1 pointing to 2. Yeah. Um is there an edge connecting 2 to 4? 2 to 4. Yeah. Is there an edge connecting 3 to 2? 3 to 2. Yeah, there is. Excellent. Is there an edge connecting 4 to 3? 4 is being connected to 3. And is there an edge connecting 4 to 5? Yeah, there is. And is there an edge connecting 5 to 1? Yeah, there is right there. And then is there one connecting 5 to 4? Yep, there is, right? So here's a matrix. So, yeah. So what is this good at? What kind of graphs what kind of graphs would we want for this? Like, do we if we had a lot of vertices and very few edges, would this be a good representation? Well, if we have a lot of vertices and very few edges, this is going to be mostly zeros. So what we'll have done is we'll have reserved this huge block of memory for mostly zeros, which isn't great. it's not great. But let's look at these two methods, get edge and get neighbors. How fast is get edge? So if I have an array, right, and each of the nodes are in the array, how fast can I get edge if I have u and v? Well, let's say u is 2 and v is 5. So I do one array lookup to get to this array, and a second array lookup to get to this part of the array where I find the edge values. So get edge is constant time. It's two array lookups. All right, well, what about get all of my neighbors? Well, get all of my neighbors if I have, if say I want to get all of the neighbors of 4, meaning all of the things 4 connects me to, I go down here and then I scan across this. I just scan down this array, right? So I'm going to have to make one look. So what does this scale to? It's however long this list is. What determines how long this list is? How many vertices are in the graph, right? If there's a lot of vertices, then this lookup will take, this scan across here will take a long time. Okay, so that means that the performance of get neighbors is v. It's just however many vertices there are in the graph. However, the thing is horribly space inefficient. Sometimes we give a project in this class, which is a sparse storage of this matrix, meaning you only store where there are edges and not where there aren't edges. And you can actually get this down from being quadratic storage to being linear storage, which is pretty nice. So yeah, so that's one possible graph representation. All right, here's a graph flavored would you rather. I told you I love them. So of course there's going to be a graph flavored would you rather. When you meet someone, you know all of your interpersonal connections to them up to a degree of 4, or you can make any food taste like a single food of your choice, for example, bacon. So this is either playing, what is it, 7 degrees of Kevin Bacon, or you can make any food taste like a single food of your choice. Now, what that means is when this power is bestowed upon you, you pick a flavor profile, and then at will, anything you eat, you can like mentally say, I want this to taste like that thing I chose, and it will taste exactly like that. So it will make anything palatable. So yeah, this is a difficult one. It's a difficult one. So a pause. Oh, okay. I hope that was a scintillating conversation. Um, so let's talk a little bit more. Wait, where's our? Oh, we didn't talk about adjacency lists. So let's talk about those. So rather than have a big 2D array, what we can do is we can just have a list of vertices, and then each vertex has a linked list of all of the edges that point out of it, right? So I would have you'd have a linked list of vertices, and then a list of all of the nodes. Like you'd have a list of node pointers. Each one would have a list of node pointers that point out from it. So basically, you could store it in an array or things like that, right? And so what adjacency lists give you is they allow you to store graphs with smaller numbers of edges, right? Because unless every vertex is connected to every other vertex in a graph, then adjacency matrices aren't very memory efficient. Whereas if you use an adjacency list, you get higher memory efficiency. And then so then we have to look at our performance. Well, if we want to get an edge, right? So if we wanted to get an edge for this, it was a constant time lookup. If we want to get an edge for this, we have to go to use entry, and then we have to scan a list of edges to find out if there's an edge to V. which means if there's a lot of edges, this will be bounded by E. So this would be big O of E, whereas for an adjacency matrix, it's big O of constant time, big O of 1, right? Now you're like, well, I could do some optimizations where I make it a hash table of edge pointers and blah 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 blah. Yeah, you can optimize both of these a bit, but if you're just using lists, you're gonna get big O of E performance. So then what about get all of my neighbors? Well, get all of my neighbors is really fast because you just go down to that vertex and then you have a list of all of its neighbors. So it's if you have a linked list implementation there, it's arguably like either constant time or big O of E as well because so it's faster when you're doing these neighbor operations as well. So but the main takeaway is that adjacency lists, while a little bit slower, are much more memory efficient, and they work better for graphs that have more vertices and less edges. Whereas adjacency matrices, you want to have what's called strongly connected graphs where most of the nodes are connected to each other. All right. So let's come up with a little bit more terminology. A A path between vertices u and v is a series of vertices and edges that connect u and v. So, if I go back to this graph example, if I wanted to say give me the path from 1 to 4, I could go 1, 2 hops and get to 4. If I wanted to say give me all the paths from 4 to 1, I could do 4, then to 5, then to 1. Though we have to be careful because another valid path would be 4 to 5 to 4 to 5 to 1. Or another valid path would be 4 to 5 to 4 to 5 to 4 to 5 to 4 to 5 to 1, right? So what happens is we can get caught in going round and round and round because these two things are connected to each other. So, if a node can be if there is a node that can reach itself through a path, that node is part of what's called a cycle. So if I wanted to go from 1 to 3, I could go 1, 2, 4, 3, or I could go 1, 2, 4, 5, 1, 2, 4, 3, right? And so we have to be careful of these things. They're called cycles, which is a path from a vertex back to itself. Cycles are kind of the annoying edge cases of most graph algorithms where you can figure out fairly quickly how to do something, but then you have to add in cycle detection because you can easily get caught in these. They're like actual infinite loops. Like they're infinite loops in your data structure. And so you have to, when you're designing these algorithms, take cycles into account so that you can detect them and ignore them and keep on trucking. A graph without a cycle is acyclic. So any graph without a cycle is acyclic. Trees are acyclic graphs. They can't have a cycle. What rule prevents that? Well, the rule is none of your ancestors can be your children. So, right, like you can't have a parent pointer that points down. And you right. Or rather, you can't have a child pointer that points up. That's the better answer. I was like, huh? Yeah, you can't have a child pointer that points up, right? So graphs are acyclic. There's a common kind of graph that's used as a directed acyclic graph. And what directed acyclic graphs look like and really what they accomplish is they're the same as trees except that each node can have multiple parents. But its children, none of their children can be ancestors because that would set up a cycle. So there's interesting things you can do with directed acyclic graphs. Um, all right, so let's write a depth first search. So first let's write an adjacency matrix, then we're going to write a depth first search. All right, here we go. Completely blank terminal. So we're going to be, for the sake of speedy line coding, doing this all in one file. So what we're going to do, we're going to make class graph. And then in here, first I'm going to be using namespace. You know, all the internet. Ah, you're a bad programmer. If you see whatever. Okay. So we're going to make a graph G. I'm going to do g.add vertex 1. And then I'm going to do g add vertex 2. And I'm going to do g.add edge 1 to 2. Or actually, you know what? We're going to make this even easier for us. We're going to do for int I is less than 10. G.add vertex I. Okay, and then we're gonna add a bunch of edges. So we're gonna add one to two. We're gonna make two. We're gonna make three go to two, four go to three, um, four go to 10. Oh wait, there is no 10. Four go to 9, and 9 go to 2. Okay. All right, so here's our test, and then we want to say if get edge 3 2 see out past. Okay, nice. So now what we're going to do is, so we've written up our test, excellent. So we can test as we go with the greatest of ease, flying through the air. Okay, so now we're going to have private, let's do adjacency matrix or list. Let's just do the list. So for that, we're going to definitely need nodes. So get some friendship going here. And then we're going to have int ID for the node. And then we're going to have a we're just going to use a vector. Did it freeze? Oh my gosh, it's having a conniption. You can't find vector? It's thinking. Aha. Okay, fine. Okay, nice. So now I'm going to, in my private, have a vector also of node pointers that is my nodes. We could also call them vertices. Like I said, it's kind of used interchangeably. So now we're gonna add this. This will be vertex ID. Okay, so what I'll do is node equals node to add equals new node, And then we'll put a constructor in like that, and we'll set okay. So node to add, this needs to be a star, equals new node, and then vertex ID. And then we'll do nodes dot, and it's pushed back to add. All right, nice. So now I should be able to add, those vertices should all go in. Now I have to do a add edge method. So oh no, sorry, from ID to ID. Oops, int to ID. And then we'll do so for I think we can do I think we can do four eaches in here. For auto node in nodes. We can do if node dot ID equals node dot ID equals from ID uh let's assume duplicates are okay, and we'll just do node dot pushback uh oh, but I also have to get the node. Oh, if not from node or not to node. Do these need to be in brackets? Pretty sure or is the lowest order of operations. Let's be paranoid. We make everybody memorize it 201 and I always forget it. Shh. Don't tell 201 students that. I forget it all the time. Oh, I'm so bad. Okay, I just put parentheses. Uh, so let's throw an exception. Why? Because somebody. What happens is it means if these are both still null, uh, um, if these are both still null, that means we couldn't find them in the graph, and so someone's trying to get us to add an edge between two IDs where one of them doesn't exist. Um, so we throw an exception in that case. Otherwise, we just go ahead and we say from node dot neighbors, or it should be error neighbors. Push back to node. And then finally, we can do get edge. So we should test as we go. So let's Let's just see if it runs. Let's just see if it runs. Um, it ran. Hooray. Okay. So now we're gonna do get edge. And so we'll do this. So int I. So get edge, this will be from ID. And this will be to ID. Okay, and what we can do here is just grab this. What is going on with my curly brackets? I must have messed something up. Uh-oh. Oh. Okay, weird. Okay. If neighbor.id equals to ID, return true. Return false. Yeah, this is, yeah. Cool. All right, so we're gonna run it. We're definitely gonna get a memory leak. Passed. Except we know we're leaking memory because we need to deallocate all this stuff. Um, wait, does the vector take care of itself? We need to deallocate the actual like nodes themselves though. So what we're gonna do is we're gonna add a alt insert destructor, and then we're gonna say for auto node in nodes delete node. That should take care of it. Now you're seeing me use auto here, and you're like, what sorcery is this? This is how you do a for each loop in C++. Uh, auto's great, except just be careful with it because you have like auto reference here. Reference meaning that like I can modify the thing that I'm getting out of this. If you don't put this in, then you can only read the value. You can't edit it. So that's a thing. Um, this makes it so that the copy constructor isn't called. Okay. So auto will just basically allow the compiler to figure out what type should be put there. So I could also do auto here, right? And the compiler will be like, yeah, I can figure it out. It's going to be a node pointer because you're calling new node. So this is going to be a node pointer. So you can put auto there. It's a shorthand. However, you can't put auto here because it doesn't know what kind. Well, does it? I don't think it knows what kind of node it's dealing with. So I would leave node pointer there. Um, anyway, it's something that will allow you to write a little bit more succinct, and you get to use for each for vectors and things like that. So I forget what you need to define in a class to make it for eachable. It's probably an iterator of some sort. So yeah, uh, let's run this again. Nice. All right. So our test passed, and so now we have to ask, well, how do we do a depth first search? Well, so the problem is you want to keep track of what nodes you visited because if you're being asked to visit a node that you've already visited before, that means you're in a cycle. And so what depth first search allows you to do is um do something like does path exist from uh let's see 4 to 2. Okay, so what we can do, this is going to be recursive. I'm going to write one that isn't sensitive to cycles. And so then you might get a question on the homework uh, that asks you to write this while taking into consideration possible cycles. Or no, from ID to ID. Okay. So we have from ID and to ID. And then, what the hey? So then what are we going to do here? Hmm. Hmm. So the first thing is we need to get the node object, which we've just written this loop. So or actually what's even better is we'll write a helper function. So we'll do node, all right, we can use auto here. So from node equals get node from ID. I should probably like, implement this. Uh, and I could refactor this code up here to use it, but I don't feel like it. So I'm not, because it's live coding. Okay. So from node. So then what we're going to do is for auto reference neighbor of from node neighbors. Uh if does path exist from ID. Wait, no. For neighbor na- na- neighbor. Oh my gosh, I couldn't spell neighbor. I was in that moment where you're like, I've spelled this word 8 times just now. How did I forget? How did I forget? Neighbor, how to spell you? No. Okay. So from neighbor to whatever to ID is. Oh, and we don't want neighbor. We want the neighbor's ID. If that path does exist, then return true. Um, and then down here, return false. Oh, yeah, this should be why. Oh, heck no. I'm not that fancy. I'm not using Clang. Are you kidding me? Okay, so we want to say, is there 4 to 2? We've connected 4 to 3 and 3 to 2, so we want to say, uh, if does path. I don't know why buttons just clicked. We're just going to call, So there should not be a path from 9 to, well, 9 goes to 2, but 2 doesn't connect anything. So there shouldn't be a path from 9 to 1. And then we'll just write my assert. Okay, so let's run it. Connective failed. Uh-oh. Uh-oh. Wait, 4 connects to 3 and 3 connects to 2. Ruh-roh. All right, let's see. Oh yeah, I want to debug now. All right. So it's from 2 to 4. Wait, what? Huh? From 4 to 2. Oh, they made these they switched the order here. Why did you do that? So from 4, so from node has ID 4, and then we're going to say neighbor has ID 3. Okay, so now we expect to go in here, and now we're going from 3 to 2. Oh, right, we don't have the base case. Ah, whoops. Thank you. Thank you, Sea Lion. Thank you, Sea Lion. Gather around, Sea Lion. Oh, can we just go, go, go? Does it work now? It passed. Yay. So yeah, we needed a base case there. So this is depth first search. Why? Because it's kind of going as far down the path as it can. Rather than looking like one chunk along the way, it looks as far down the path as possible. To make this so the thing that's nice is that when there's no cycle, we're good, right? But if we have 4 connect to 2, 3 connect to 2, but if up here we have 3 connect to 4, if we just add that, and then we run this again, we have a segmentation fault. Because look how deep we've actually just blown out the stack with recursive calls, right? Because it's just going back and forth between 2 3 2 4 2 3 2 4 2 3 2 4 2 3 2 4 over and over again. So we need to be sensitive to cycles. Um and so there's a number of ways to do this. One is to pass around a list of places you've already visited, and then before you make that recursive call, you check and see if the place you're trying to go to next has already been visited. The more efficient way, I believe, is to actually keep a stack or a queue of places that you want to visit next and do this a bit more iteratively. But anyway, I just wanted to give you an idea of like what graph structures look like and how you're hopping around and looking at different paths and how it's all just a big connect the dots. So yeah, that's all I've got for you this time. We'll give one more assessment of the cat dog scene. Right here we got Charlie is tuckered out. Oh, he's so tired. And then we have Jules, who's just chilling. Just chilling. Just being a Julesy. All right. Have a great day.